Hello, thanks for coming. I've got two topics I'm going to talk about today. I'm going to talk about 2D analysis for determining water surface elevations and flood levels. Then we're going to get into Suda, which is a Bentley software product update. We're going to start with 2D analysis. We're just going to talk about the basics. This is an introduction. We're not going to get into modeling or how to set up a model. We're going to start by defining it. We'll talk about some of the assumptions and applications in general. And then we'll get into how this applies to TechStop, where it can help us with our hydraulic projects. So let's start by, oops. So what is 1D flow versus 2D flow? 1D flow, it's laminar flow, streamlines are parallel. Flow is flowing in one direction, forward and backwards. Pretty simple flow. 2D flow, flow mixes, flows moving in all directions in your horizontal plane, so forward, backwards, laterally, so more complex flow. 1D, simple, 2D, complex flow. What are some of the assumptions and applications? 1D flow, uniform flow, stays in the channel. Great for narrow floodplains where majority of your flow is in the channel, moving in one direction. One of the big assumptions with 1D flow is that your water surface elevation is single and constant across the cross-section. And also your velocity is constant. It uses a weighted average of flow and velocity to calculate your water surface elevation, which can introduce some error if your flow is 2D. 2D flow, flow paths are not well defined. Your water surface elevation is not constant across your cross-section. Your velocity changes horizontally. Great for situations where your flow is splitting, diverting, leaving your system. Great for alluvial fans. Also great for floodplain analysis when you have wide floodplains where you have variation in your vegetation, land use, where it can change your direction of flow, change your velocities, which can affect your water surface elevation. Here's a table which can help you select which model you want to use. This came out of FHWA's Hydraulic Design Series number 7, table 4.1. I know it's hard to see, but so basically, bottom left corner there, a solid circle means it's well suited, half circle, secondary use, and then a hollow circle, not well suited. So we'll just start with the two examples at the top. Small streams and channel flows, 1D. If you look halfway down, you've got a skew greater than 30 degrees, then you'd probably want to do 2D for that. This table can help you if you don't necessarily know which model to use. Okay, so this is a cross-section, a 1D cross-section with a 2D water surface elevation overlaid on it. In blue, you can see how the 1D is constant, level, 2D in red, solid red there. You can see how it's not constant. So is this 1D or 2D flow? In this picture here, this is 2D flow. You've got water leaving your main channel, exiting into the floodplain, and then also coming back in. So when water leaves your main channel, goes into your floodplain, you've got different velocities, different directions of flow. But if you were to take this a step forward and raise the stage above your banks, it'd go back to 1D flow because it'd be flowing all in the same direction. Another example, this is obviously 2D flow. You've got channels splitting, flows splitting between channels. This is 2D flow. So what is the approach for 1D? To represent your channel, you basically take cross sections along it, and then also your reach lengths define that channel. So you would start with a known, either upstream or downstream, and then calculate to the next cross section, velocity, water surface elevation, and you do that successfully until you get all your water surfaces at each cross section until you get a profile. 2D approach is you'd have a terrain that represents the entire surface, you lay a mesh on it, divide your mesh up into cells, and then at each cell you'd calculate a velocity and a water surface elevation. So it gives you a complete picture of what's happening. So these are results of a 2D analysis, and you can see your velocity vector field. You can see where your water is flowing, splitting in the top picture. You can also see where your velocities are high in this bottom picture in red, and then blue where your velocities are slower, where your ineffective flow areas would be. This would be very difficult to determine in a 1D analysis. I basically just talked about this slide, so I'm going to skip it. So what are the advantages and disadvantages of 1D? It's difficult sometimes to lay cross-sections, especially if you have a bend in your river. Cross-sections can't cross. You lay your cross-sections where you have inflection points, where you have changes in slope, where you have changes in cross-sections, shape. Also, 1D does not capture complex flow. You're just looking at one direction. It also possibly overestimates depth and velocity. It may underestimate it also. And it's also difficult to estimate ineffective flow areas. Advantages are if you validated your survey and you need to make a change in your cross-section, you can lift your cross-sections up or down very simply. Since you only have a few cross-sections, it's faster to compute. You have faster computational times. It computes hydroxy structures very well, and it's easier to troubleshoot. 2D, it's more data intensive. There's more data points. There's more data points, more calculation points, longer computational times. And also another drawback, especially for us since we do a lot of hydraulic structures, it doesn't do hydraulics computations through bridges and culverts very well. I'm sure that we'll be improving that here in the new future. And there's less user experience. There's less shared knowledge. Advantages, again, it models the surface flows very well, split flow and diverted flows. And also calculates your ineffective flow areas for you. You don't have to estimate. There's no cross-section placement. There's no guesswork in that. And then it's just more informative. It tells you where your flow is going and the velocities. And then, of course, the dynamic mapping. All right. Of course, at the end of the day, I'm going to put those advantages and disadvantages up there, but criteria for selecting 1D or 2D is does it add value? Okay, so how can this help TxDOT? So split flow, if you've got a roadway with several culverts going through it and several drainage basins, and you've got flow splitting between basins, a 2D analysis is great for determining that. You can do it in 1D with lateral structures or a rating curve, but that can introduce some error. Another example where this can be applied is in the wide floodplains. Again, we have variations where flow is changing direction, velocity is changing. And then in urban areas, we have multiple flow paths. 2D can capture that very well. Or if you just want to inform your 1D model, you want to know where your effective flow areas are, do it in a 2D, and then put that back into a 1D. And here's just a schematic of what I was just talking about, where flow is splitting between basins. 2D can account for that flow. And here's another schematic showing complex flow in an urban area. You see where your problem areas are, where it's flooding. And then here's 4 softwares that are widely used. There's a lot of user experience with it. The 2 that are highlighted there, they're free, and they're also just have a good track record. TxDOT policy and guidelines. Right now, we don't have a formal policy or guidelines for 2D analysis. If you have any questions, you can give us a call. But also, there's guidelines that FHWA put out and FEMA. All right, next topic. I'm just going to talk about Suda, which stands for Subsurface Utility Design and Analysis. This is a Bentley product. It's a update. Geopack drainage is going away in about 3 years. This is the replacement to it. So we've been doing 3D models for roadway design. Suda is 3D drainage design. So this connects the two. There's 2 components to Suda. There's a utility conflict detection component and also a hydraulic design component. The utility detection component, since we're working in 3D, you lay out your network in 3D, put your utilities in 3D, and it'll spit your report out showing where all your conflicts are based on your tolerances. So I just said that this Suda replaces GeoPack in about 3 years' time. StoneCat is the hydraulic engine that does the calculations. It could be used standalone if you don't want to do a 3D model, set up a 3D model. You can do this in 2D rather quickly. And some of the upgrades, one of them is it's got a versatile project manager tool. If you want to do multiple design scenarios, alternatives, you can do it all at the same time. If you want to change your pipe size, or if you wanted to look at future land use, you do it all at the same time and then compare it in a summer table, instead of having to run different files like you would do in GeoPack drainage. One of the drawbacks right now is that it does not generate sheets, but we did verify that it'll be able to do this early 2018. Oops, did I skip this? So when you lay a network out, you put your pipes in. Those are pretty standard, but all your nodes, which is going to be your inlets, your SETs, your head walls, those are all custom to TxDOT standards. So right now we have to build those cells in 3D. We're doing that. We've got 3 consultants on there helping us with that. We've got 50 TxDOT standards, and from that, about 4,500 cells are being generated right now. And the target date to get that done is summer of 2018. That's all I have. If you have any questions, you can contact our team. Appreciate it. Thank you.